how to get to it. And as I mentioned, also provides exemption for economies, which is really good because that's what we do. Everybody in this room's here for that. Now, the rule that says you can't take a green change is somewhere around $200,000. Okay. The neat thing is the way the wording is, it says deals with the production of any bright light into airspace. Airspace is pretty much defined, legally defined, from the ground up. So any bright source can be determined for that. So you see those spotlights that show off at car dealerships and stuff, you're supposed to have a permit. Or they can be fined because it falls into the same thing. And as a requirement, they have to apply for the permit to project into the airspace. The permit that's attached to that regulation, if anybody's ever seen it, is extremely complicated. It was originally meant for, if you ever seen the laser shows they do on Parliament Hill on July 1st, that kind of thing. It was never intended for people doing astronomy saying, look at that thing over there. You know, like a Jerry Sky binocular. Okay? It was never meant for that. Fortunately, Transport Canada recognized that. And they reached out to the RASC and FAQ to talk about and say what we could do. So, we went through a process last spring, worked with them, worked through some, really and truly what we ended up doing for the most part was taking what the RASC always had on their website as recommended practices and basically turned them into, eventually they will become policy and will be found in the RASC policy manual, but procedures to be able to use the permit. So in order to use the permit, you've got to comply with these, what's on the permit. Part of the problem when we worked with people across Canada is, again, education, getting everybody to understand. Transport Canada issued a permit based on what we already said we were doing as a society. Some people think, well, Transport Canada come in and said, you got to have spotters, you must have it, you must have that. Well, no. What it was is all the stuff was more or less already on the RASC website, on the laser pointer, on the laser safety portion we had, and we just turned it into conditions in order to use the permit that Transport Canada is giving us. So, first, must be an adult 18 years or older. If you're under that age, you cannot use these things at an RASC event. Okay? Regardless. There's no way to even point it out. You must be an RASC member in good standing for at least 2 years. So, RASC, it's funny. You put that out there, a member in good standing is used all throughout all sorts of policies in the RASC, and then somebody said, what does that mean? So that's now a great debate going on in the National Council of the Board. Well, it's not a bad thing, because if you say you got to be a member in good standing, you should know what that means, right? Because depending on everybody has a different interpretation. For our membership here, basically, you haven't been booted out of the club. It's the simplest way to look at it. 2 years membership, okay, in the RASC. The primary reason behind that is actually very simple. We want to prevent somebody off the street getting a membership, going out and not following the safe laser practices, lasering an aircraft because they don't know they're not supposed to, and now the RASC is the one that looks back. If somebody's been in the RASC as a member for 2 years, they've probably been exposed, if they were new to astronomy, to safe and correct use of green lasers. I know every time I've been at an event, we try to take 2 minutes at the beginning just to educate the public on why we do things the way we're doing it. Okay? And to get some more information out to the public about safe use. And that there are rules and regulations that enforce that. And finally, you have completed this training course successfully in the past 3 years. So it's got a 3-year limit. 3 years from when you do the training, you have to do the training again. Make sense so far? Good. Okay, so we hold a global permit for for the use of green laser pointers outside of the 10-kilometer zone around certified airports. So, simply means interactive map has all the certified airports in Canada. You click on that dot if it's around an area you are, because it just expands out a really nice map, bring it right down. Locally, Spruce Woods is outside, is an area that's safe to use. Birds Hill Park, one area in Birds Hill Park where we tend to do our events is legal. You have to be careful because parts of a good chunk of Birds Hill Park is not, or is within a 10-kilometer zone. And Oakanic Marsh. So those are the three places traditionally we do that. If you do it anywhere, if you want a permit inside and run an event inside, you can apply. We're trying to educate everybody because they say, oh, I can't do it anymore. What we've done is if you use what the permit requirements are for ours, plus whatever you were doing before to get away with doing it around an airport, until Transport Canada, you're probably going to get a permit. And you don't need to get one every single time. If you know you hold an event, let's say we decided we were going to do an event at Assiniboine Park 4 times a year, we could apply for our permit, and if we're approved, it would be approved for those 4 events. So Transport Canada has come a long way from where they were just 2 years ago. And again, it can be found, I tried to link to see if it works, but we're not going to because I know it doesn't work. So when it does get back up, I've notified transport. You simply open the map, expand it to your location, confirm you're not in the affected area. If possible, you should record your GPS location to provide with your final report for the event. So, before you hold an event, you have to send a notification to the center executive at least 8 hours prior to the event. Again, we're trying to look for the best way to keep it simple for everybody. 8 hours before the event, you should know that you're going to do something, or plan to do something. So, you send an email to the executive. The executive is going to, if you don't hear back from the executive here at Winnipeg Centre, you're considered approved. We have a list of who's trained. As long as you tell us most people are on the list that are trained, it's approved. Okay? And in theory, we know we're going to have a public event that we're going to be able to send off. So just remember that. If any of the executive have a question about it or aren't sure the person's called or current, then we would ask some questions to clarify. Okay? So, when you let them know, you got to tell us who the spotter is going to be and who the pointer is. All right? Ideally, we know that. We're going to also, if it's an area that's really busy, maybe the executive might come back and say you should have 2 spotters, depending on the locations. Don't know. It's not likely to happen. It also allows us to just continue to confirm that everybody is certified. So, you do need to have a copy of your membership card, because that's the only way you can prove you're a member in good standing. Because if you're out at Oakanic, and let's say Oakanic's closed, you're doing fun stuff with that, you do have a spotter out there. But there are some people, and they say you're breaking the law. You say, no, I'm working under the permit that the RASC has. And they say, show me proof you're a member of the RASC. Your membership card is the only thing you got. Right? There's nothing, no other way to do that. So remember that. An insurance copy can be requested from the RASC website and the member side. You should be able to go in there and you can actually print off a copy of the liability insurance that's there. However, when we did the first thing and we sent in all our documents to Transport Canada, they hadn't updated it. In fact, it was a month overdue. So it's funny what happens. So when you're doing it, only a green laser pointer of 5 milliwatts or less can be used. So not much more than this. Where does that come from? Health Canada regulates this. And they've determined anything larger is a public health hazard. So yes, there are lasers bigger than this in Canada, but they will be licensed by Health Canada. Okay? They're called, the class they fall under is a 3A or 3R. And the thing that you need to understand, a green laser pointer of this size can cause disorientation to aircraft and crew when exposed unexpectedly, and it definitely is a major concern for aviation safety. I am in the aviation industry. To train our crews, to give them an idea, we took a video on the ground where we ran this laser line in my hand, just on the windscreen. I took a picture on the inside, and it's pretty amazing. It's very blinding. All right. So if you imagine you're coming in over Old Marsh, outside the 10-kilometer range. If anybody's been out there, know all the approaches are right over the hot marsh. It's actually the area, one of the places they call it when they get there. And you make a mistake and don't see him, and you zap him. That's in the critical phase of flight because it's on landing. It's a really critical phase of flight. They're disoriented, and it's not a good situation. And that's the #1 concern that Transport Canada has with green lasers. I don't know if you've heard recently, the person, they got 2 weeks in jail, and I think it was $25,000 fine. It was about 6 weeks ago. So they are taking it serious. And that was the first one where they actually got jail time and fine. So it's interesting to see that they're now enforcing it, and that's going to get the word out a little more. And yes, I know, you can go out and buy off of Amazon and have a laser of 1 billion wattage. It just depends on whether or not Canadian Border Services picks it up or not. Okay? You are breaking the law if you try to bring one in greater than 5 milliwatts. Spotter will be used at all times. The green laser pointer user will determine how many are required, but a minimum one is always to be in place. So that's part of the reason we want to know who's going to be the person using the laser and who's going to be the spotter. Because the laser person is the one that's going to be accountable if something happens, which it should. As long as we follow everything we do, all the times we've done it, there should never, ever be an issue. Okay? But if they're the one responsible, they have to decide whether they want 1 or 2 spotters, or as many as they require. Spotters got to be in position to clearly absorb, it's been a long day. Observe where the green laser pointer is being used and watch where the aircraft may fly into. For instance, again, I keep going back to Old County, which is one I'm most familiar with. Depending on the winds, the planes are always flying in exactly the same locations, which kind of helps that you're on the approach line. If the winds are coming that way, if they're not, they're coming out in another direction. But you can see where the planes are, and you can see where you need to put your spotters. How do you tell? Look at your position lights on the aircraft. They're green, red, and white. And usually you see the flashing light as well. Sometimes people say, well, how can I tell it's an aircraft? Well, anybody else who are astronomers, even amateurs, we look out. If it's moving, it's probably not a star. Not guaranteed. Probably not a star, because aircraft, even when they're far away, still moving. It's more than you're going to normally observe in the evening, right? It's faster. And with a very minimal amount of time, you're probably going to pick out that there's different lights there, especially if they have the strobe lights on, which they should have. So those are the ways you pick it out, and you know that's important. If you're spotting, be very, very careful. It's easy to stay focused on that airplane. We're doing a talk over here, we miss the plane that's over here. Okay? You got to keep moving your head, scanning, looking up and down, doing all sorts of things. It's not easy. And it's probably a good idea to have more than 1 spotter just to trade off if you're going to be any length of time. When it's all said and done, you got to provide a report. This is a condition of the permit. We have to submit a report once a year to the National Executive. So again, that's why it's good that we want you to notify the Center Council. The Center Council knows an event happened. Hopefully when your event's over, you just send a quick email, everything went great. By the way, we had 25 people at the event. Now the Center's got the information we need to submit a report on how many people attended. And big thing here, if you want to keep the permit, report the events. Because the same info, by us telling Transport Canada how many people across Canada we use the permit for, it justifies them spending the time and money, because they do have to put resources to it, to issue the golden permit. Make sense? All it is once a year we send in a report. We have to send in a report as a council anyways on how many public events we do. Now we just have one extra thing to report. That's all. Any questions? Remember, you're responsible for compliance with the permit. We are covered by insurance. All right? Insurance knows that the permit's part of this, our insurance providers, but you're ultimately responsible. So, to my knowledge, there's never been an RASC event, even before we knew about having to have a permit, there's ever been an accident where somebody's hit a laser of an aircraft. So the risk is extremely low. Transport Canada knows it's extremely low. We have a way to be in compliance with the regulations and not break the laws. We have an opportunity to promote the public and educate them about safe use of lasers and also what the rules and regulations are. And if you are doing an event, always take, like I said, 2 minutes at the front, just briefly talk about it. All you really got to say is, did you know this laser that we're going to use for this is unregulated? We have a permit from Transport Canada to use it. That permit restricts only members of the RASC or other science bodies to do that, to use this. And the size of it's regulated by Health Canada. It should be 5 milliwatts or less. Anything larger is considered a health hazard. We just did a 30-second public service announcement to everybody that we come in contact with. Any questions? Yes. Oh, wait, up there. Sure, go ahead.
What's the distance a green laser pointer extends to?
For the 5 milliwatts, oh gosh, you asked that, I didn't look at it. It's really not that high, okay? So, in theory, don't quote me on the thing, this where it would cause a problem with an aircraft is probably 3,000 feet, okay? So hence again, on the approach, if you know anything about approach when they come in, you're in that band. And that's why it's picked, 10 k's out is usually where they start the approach. And so those kinds of things, depending on the aircraft, there's lots of different factors go into that. So these could be that problem. Anybody who's taken, you could take 2 of these, exactly as they look the same, they're 5 milliwatts, put them together, and shine them on that wall. I don't have another one. You're going to notice something. They're going to be different. It is not a science on what these, how many milliwatts these are, because they're not normally individually tested. So just be aware of that as well. If the sticker says it's 5 milliwatts, it's 5 milliwatts, right? Nothing in the rules say you have to test it if you have one. But if you don't have a sticker on it that says it's 5 milliwatts, or a class 3 laser and that sort of thing, then you need, then think about it. That's all. Big thing we want to educate too when kids are around, it's not a toy. Anything else? Okay, so for those who have been here for 2 years and have not done the exam, can you put your hand up real quick? Perfect. You'll see it's an extremely difficult exam. Again, you have to hold your hands up here again. Okay,
What we have lined up, we'll begin. I have a number of new announcements I'd like to mention. I can change at this time. Of course, lots of pizza. Okay, calendars. Jewel, how many do we have left?
We still have six.
Six left.
Six calendar,
Okay, I think I have to get mine, right? So I have to
including
reserve
yours, yeah.
Okay.
Yours and mine, so
Okay,
six
everyone
only.
All right, so see a Jewel for the calendars. We have only 6 left, so we're going pretty fast. Okay. Well, okay, U of M, open house. Okay, there's nothing for this month, but according to Danielle, the planetarium is being renovated and it should be and also upgraded for next year. So I'm looking forward to that. So we're going to have to use room 240. So it'll be really exciting to see how that's going to turn out. So yeah, nothing for open house this month because it's Christmas. Oh, come to March, there is something, December the 19th. Constellation, winter constellation. So I'm planning to make it out that night. Thursday, I get Friday off again, so won't be an issue. If you bring your telescope, the fee gets waived, so you don't have to worry about that. But it's a nice way to spend some time and do a little astronomy too at the same time. Next, potluck. We have determined to be January 18th, which is, I think, it's a Saturday, 3rd week in January. Email notice will be sent out. We'll determine the location, and yeah, potluck is really good. It's another good time to spend some quality time with your friends, and just enjoy everyone's company. Website. I'm really excited to this, and we're working on it around the clock for most of us. We just spent, well, probably a good $500 to improve the functionality of it. We added some new features, and I know some people are testing it right now, including myself. So it should be ready as early as January, I believe, but don't quote me on that. But we are testing it this weekend, so I'm really excited about that. It looks really, really good. So we're going to have a lot more functionality, and it'll be nice access and have all the information to Winnicentric, pictures you can post to, and all that. So it'll be really exciting to see how that happens. Sorry, Sam, you're next.
Yeah.
He wants to talk about this. We're expanding our horizons, basically.
I just have one slide, so I shouldn't need this. Yeah, so it's my first time in front of all of you. It's a different perspective up here. I like it. So we are now on Instagram. Who out there is on Instagram? Show of hands. It's a few of you. So get your phones and look up RASC Winnipeg and give us a follow. You'll see that our portfolio is not super impressive right now. We have a single picture. But I know that we have a lot of really good photographers out here in the audience. So look out for an email in the coming, the next couple weeks or so. I'm going to be doing a call for submissions, which is we want pictures of mostly of past events. The Instagram page is a push to get more membership, more people to discover the club and come here and really enjoy what we all enjoy. So we're looking for pictures of events. If you have them, that would be amazing. We're looking for some astro photos that you're proud of, and a little bit of information on it. So if we post one of your images, you'll be given credit. We'll have a link to whichever social media or portfolio site that you want us to link to. And yeah, you'll help promote the club and hopefully help us boost our membership. So look out for that email, and I hope to see a lot of really great images from you because I know you have them. So thank you.
Thanks, Sam. All right, now I get to talk about the Facebook account. It's been a while. It's been on for a while, but we haven't used it for some reason, and then we finally decided to talk about it at a council meeting. And now, thanks to Scott, I got golden rights to it. Now I can go with changing it. Primarily, the Facebook account was supposed to promote the activities of our club, any events that we have. It was more geared towards the media, for example, the news, right? So apparently some news at the time. If they want to search what's going on, they can always come to us. So of course, we also thought about it, and of course it's still debatable. Club members, if you want to post something, you're heading out somewhere, or doing something, or planning something, that's what it's there for. So I have only one picture I posted this morning, and that was it. But I did post about today's meeting. So again, it's a great way, an alternative way to the email list that we have. So please check it out, and it is active right now. So, okay, and of course we have the RASC email list. Some of this, Jay kind of mentioned this. We're going to start putting this out on flyers here, so people can go and grab it, and I won't be repeating myself every single time. Okay, Explore the Universe. I want to put this up because Dennis is here. So if you have any questions about it, it's a great way to explore. If you're new to astronomy, if you want to get into it, it's a great way. A lot of people are using it. They come to their lead, and they work on their Explore the Universe, and you get a certificate at the end. I do know 3 people have completed it already, and we mentioned Lunacentric when it comes out. So if you wanted to start doing this, please see Dennis, who is here. Okay, thanks, Dennis. Okay, all right. Another thing, telescope loans. Abdul, who's handling the calendars, is also doing the loaner telescope. So I don't know if we have any telescopes out or available. Do we, Abdul? Nothing?
Abdul. Nothing.
Nothing?
All
Okay.
of them
I just want to
outside.
see it because I think they're all signed out. Okay, I just want to make sure. Okay. All right. That's just some telescopes that we do have for the members. It's a great way if you haven't bought a telescope or you're looking towards buying a telescope. It's a great way to, of course, check it out and see what we have. The PSC is great for looking at the sun in real time. And of course, now we added the tracking amount to it. Glenn Lee Observatory. That's me. I'm also the director of Glenn Lee. And of course, another thing that we're also doing is upgrading it and trying to keep it more modern. As I keep mentioning the fact that this telescope is remote. You can control it from the warm room and also the dome too. So again, I'll be happy to train people on it. But we won't have anything this Saturday because I decided because it's too cold out right now. And of course, Christmas, I think it's better to stay safe and warm with your family and friends. So like I said, Saturday is canceled, so we have no observing. I'm not even going to schedule it for next week after that. So, all right, what else? I think that's all I have to say. Next we'll have What's Up with Jay?
You're always wondering that.
Whoa, what's up? Look at this, we get to change over a new year. You know, there's nothing up this way. All the planets are behind the sun. It's too cold. It's too cloudy. So we'll have to do what we can. So, Christmas. Oh, I forgot to put that on the list of stuff. Just a little picture of what's there. This is midnight tonight. And it's a time of year when you have what is normally considered the best parts of the Milky Way gone for the winter, although you can still pick them up in the west. Oops, that's not where I want to go here. In the west, earlier in the evening. So we're looking at the winter Milky Way here, which looks really good on this diagram, courtesy of a few enhancements, but it's really not that bright. But we have some actually spectacular things in the winter because there's a very nice constellation. In particular, Orion, which at midnight tonight is pretty much due south, about as high as it gets in the sky for us here. And of course, Orion has right in here, underneath the 3 stars, the Orion Nebula, which is the brightest nebula that you can see from our latitude. And it's a very nice object in binoculars, and a very, very nice object on a 48-inch telescope as well, but we don't have anybody that owns one of those here. You have to do it. It's, we've never seen the Orion Nebula. We've got to get out in one of the Saturday Edward only nights at Glenley and have a look at it through a 12-inch telescope because it is kind of mind-blowing. And one
to go with binoculars on these sorts of things, and in particular Oregon, up in the north here, in the northern part of the Milky Way. You could ignore this thing here, that's the moon, which is an annoying little feature of tonight, for reasons I'll make clear. But up in Oregon, we have a number of what are called open clusters. Those are loose connections of stars all together, very, very colorful. There are other ones up in Cassiopeia. And if you're a little bit inclined to photography, this is just a wide-angle picture taken with an ordinary camera. I don't know what the person who did it used, but this is the sort of thing you can easily do, and even pick up ambulance in a camera just by shooting it off of a tripod. So for casual observing quickly with a pair of binoculars, Oregon and constellations both to the north and south of it have some very nice open clusters. So we'll talk about the suns. There's no sunspots. I told you it was going to be a very interesting one. This is now the 30th day in a row with no sunspots. 31 days ago there was some tiny little one. And we are approaching a record, according to the spaceweather.com, for the most number of days in a year without sunspots. So 100 days with sunspots, less 20 or so we've got to go. Well, that has a bearing on things like aurora and stuff like that. We have seen evidence that the next sunspot cycle is starting to build. Now, sunspot cycles go up and down in an 11-year cycle. We're very close to the bottom of the current cycle, cycle number 24, and it's expected to bottom out about this time next year and then start increasing again. And so the way you tell whether or not some of the sunspots that are appearing belong to the old cycle or the upcoming new cycle is the pattern of their magnetic field. Typically, you'll have a negative magnetic field leading and a positive magnetic field trailing, and when it's a different sunspot cycle, the pattern flips over. We've seen 3 sunspots so far with that reverse pattern, which tells us that while we're getting rid of one sunspot cycle, a new one is brewing underneath the surface of the sun as magnetic fields get all twisted up. We do have one event. Thing about the sunspot cycle is that it doesn't mean there's nothing happening. There's actually been a couple of pretty decent auroras over the past month. Right now we have this stream of solar particles coming off of the sun that erupted yesterday or is currently erupting because it comes from a kind of hole in the magnetic field of the sun. And so they expect that this is a pretty strong stream, a pretty large one, because the hole is going to be pointing right at us. I'll show you a picture in a second. And so we should probably get some decent aurora. If you want to go to Burnsville Park and take a look and stay warm, then you might find you have pretty nice view. So here's a picture of the sun this afternoon. This is the hole in the sun called the coronal hole. Magnetic field is open to space there, and so particles can flow right out of the sun from that point. And it's like a searchlight. As the sun rotates and it points at Earth, it blasts the particles toward us, and we get an enhancement. Here's a map of the current sunspot cycle. We're down in here. You can see all these zeros right along here. This is the predicted minimum, which is 2 years from now, but current suggestion verbally is that it's going to bottom out right in about here and then start coming up again. Haven't had too much luck in forecasting sunspot cycles. This is the pattern from spaceweather.com showing where the auroral activity is tonight or this afternoon, and that swings around in a circle and comes down to our side. It'll be still fairly far north. If there was a coronal hole and we got some activity, this green area would expand and it would go into yellow and red colors. So if it goes into yellow, it's usually worth going out to have a look, or phoning somebody else who went out and had one and said, "Hey, what's happening out there?" Send one scout out ahead, like on D-Day, to send one guy on ahead to see whether anybody was expecting them or something like that. Planets. Mercury is in the morning for another 2 weeks, and then it goes behind the sun. It's one of the best presentations of Mercury in the sky for the year. But it means you're going to have to get up in the coldest part of the day and hope that it's clear and go look for it low in the eastern sky. Venus is low in the evening sky, getting higher every night, but not by an awful lot. It's 17 degrees high a month from now, and it's about 19 degrees high in between. So it's almost running horizontal along the horizon as it moves in its orbit, because the interaction of the sun, Venus in its orbit around the sun, and the Earth in its orbit around the sun is keeping it in a position. But Venus, as we know, is so bright that it can be sitting right on the horizon, and you can see it. Well, we know how to see Earth. And Mars is also well ahead of the sun, but it's a part of its orbit where it's not climbing high up out of the eastern sky. It's staying pretty low down, even though it's moving out farther and farther from the sun. So we won't see it climbing any much higher than Venus does. But again, Mars is not very bright, magnitude 1.5, whereas Venus is probably at magnitude 2 or so, -2, and so Mars is not going to be as prominent. It's still a long way away from the Earth, but if you do see it, it's pretty distinctive with its reddish color. Jupiter is still not into the sun, but it's so low that it's virtually invisible, or not very usefully visible, and in its conjunction on the 27th, which means that it's directly behind the sun. Saturn, same sort of thing. Its conjunction is on the 13th of January, so a month from now. And so those two are pretty much gone for the next month to 2 months. Uranus and Neptune are both pretty well placed if you want to make a shot at them, especially Neptune, which is up for a large part of the night until about 3 in the morning. None of them are really high in the sky because of their position in their orbits, but they're as high as they're going to get at 17 degrees. So you're still looking at a fairly low angle. You can take if you were to hook a camera onto the telescope at Glenlee and take a picture of either one of those for about a minute, you would be surprised at the number of moons you would be able to see around those two planets. Well, we have a Geminid meteor shower tonight, and with a bright moon out. And unfortunate, because a Geminid meteor shower is generally regarded as the best meteor shower of the year. We get the solstice on December 21, so the sun starts coming back after that. Its major point. We have another minor meteor shower on the night of December 21 and 22, and because it radiates from the Big Dipper, even though it's a relatively minor one, it's certainly high up in the sky for us, and easy to see the meteors coming out from that point. Solar eclipse that we can't see, and a penumbral lunar eclipse we can't see. And no, I'm not going to either one of them. And then we have the only thing that's sort of half decent is the Venus-Moon conjunction on December 28th. It'll look a little bit like this, with a nice crescent moon underneath Venus. Those are always a nice little picture. You know, it's like at 6 p.m. here, because if you wait another hour, both of them are going to be down here just barely above the horizon. So you want to catch that grouping. Somebody will always send it in the sky and telescope, and it'll always appear there. So maybe you could be that lucky one of the 127,238 pictures of it yet. Geminids, going back to them, this is the fireball cameras that NASA runs, and you can see this cluster of fireballs that it's picking up in with other meteor showers or parts of them. So 56 fireballs in this 24-hour period. You see 30 of them almost are Geminids. Sporadics, 21, which mean they don't belong to any meteor shower. They're just chunks of rock that burned up in the atmosphere. And then we have 6 6 of them from 3 other meteor showers that only NASA knows about. So these are actually kind of interesting to watch when there are meteor showers. They're on spaceweather.com every day and show you the collection of past days fireballs. You can see that the nominal rate is 120 per hour for the Geminids, but the moon is really going to kill things off. And typically, a situation like this, we advise you to go out really early, as soon as it gets dark, before the moon rises if you can. It's not a very long period. Tomorrow night, they'll be subsiding, but they'll still be there. You might have perhaps a half hour to an hour around 5 to 6:30 or there, where you might be able to catch some in a relatively dark sky. It's the only game in town right now. Well, except for this counter. Pan-STARRS, another one of the, 30 or 40 Pan-STARRS comets, but this is the only one that's really brighter than the 10th magnitude. It's going to get up to about 8 years to measured brightnesses, and where it's predicted the light curve is getting up to almost 8 years in mid-2020, actually, around the center of probably beginning of June there, late May. So it's coming up very, very slowly. At 10th magnitude, it's certainly easy enough for telescopes, but when it gets to 8th magnitude, should be able to pick it up in some fairly big binoculars. The nice thing about it is that it's circumpolar up near Capella right now, which is one of the brightest stars in the northern part of the sky. It's up all night long, and interestingly, although it's a little ahead of my normal time frame in these, it'll pass just underneath the double cluster in Perseus, which is another one of those nice little open clusters I talk about that most of us know about. And any time out in the dark sky, that'll have, as Jerry said, that'll get all the photographers out to snap a picture of it. And it should still be up in, well, we're talking in the end of January here, so it's going to be up in this brightness range. So we're going to be just under 8. That's a pretty easy picture. 1 minute exposure on a track mount, and you're off to it. And so you're already seeing traditional patch picture at the end. And Gail, I have to confess that I've reused this from 2005.
It's a repeat? That means there's too many.
Anyway, thank you.
Not yet.
You go back? Good? Yeah, okay. All right, for those of you that don't know me, hello, my name is Camille Hood. I'm an instructor in the Department of Physics and Astronomy, University of Manitoba. So Brian alluded to it, but there is work happening on the planetarium, which is super exciting. So the dome is now installed and completely finished, and they put in a moon surface themed, abstract themed carpet. So the carpet is in, the sound paneling is in, and so the projector should be here in the first week of January. So it's coming along finally, which is really nice, and I'd be delighted to have you guys come and check it out once it's open. So I'll be talking about some of the news in astronomy over the past month. So this image is not new. This is an image from the Parker Solar Probe launch, but some of the very first results from that mission have been released in a Nature paper last week, and I'll be discussing those later. So the headline that I will be discussing is another cyclone formed at Jupiter's south pole. So this is a fun Juno result that got a lot of press release at the American Geophysical Union that happened this week in San Francisco. They discovered an exoplanet orbiting a white dwarf, but it was a gas giant, which is kind of unexpected. And then finally, I will let NASA tell you about some of the first results from the Parker Solar Probe, but I'll answer questions as you have them. But this is really exciting. As you may know, the sun is my area of expertise, and so I'm very excited to see these results. Okay, so the very first headline is a new cyclone joins Jupiter's South Pole club of cyclones. So there was a central one and then 5 cyclones arranged around it when they first saw them in November of 2018. For the first 7 months of observations, the cyclones were fairly stable. And then for the next few years, Juno would orbit once every 2 months, and they would see little shifts in positions. Little cyclones would kind of appear and then bounce off or redisappear. And so it was a real mystery to see how stable this was. And so finally, this November, a new 6th cyclone, I believe it's this dark one, well now it's 4 and 3. I think it's the one on the right, has managed to find its way into a gap and is now a stable addition to this group of cyclones. And so it whips around. The winds are 360 kilometers an hour, which is about the same speed as the other ones, and so it's stable and comparable to the other ones. So this is still kind of a mystery as to why we would have 6 cyclones all around the South Pole. The North Pole, I think, has 8 of them, but you have these groups of cyclones that exist on the poles of Jupiter that are really stable. So there's still some open questions. So just to give you some context on this image, this is an infrared image, so it gives you heat or temperature from the Jovian Infrared Auroral Mapper instrument on the Juno spacecraft. And so the dark regions are cooler, ammonia clouds that are about 20 or 30 kilometers higher than the rest of the clouds, and the brighter regions are rich in hydrogen sulfide and are warmer and lower down. In white light, this is what that looks like. So they're not quite the same image, but you'll notice that the terminator is visible in white light, and the infrared doesn't care quite as much. But you can kind of see there are 5 cyclones visible, and the new one is this darkest circle up here. I think I've got the laser pointer. Yeah. This is the new one, and the other cyclones right here. So the question is, why do we have stable cyclones? And so a result that came out earlier this week by Cheng Li is that there seems to be a buffer zone around each of the cyclones that rotates in the direction opposite to the direction that the winds are rotating within the cyclone. And so the buffer zone will prevent each of the cyclones from merging with each other, but eventually the buffer zone itself will deteriorate due to turbulence. And so here is a short video of cyclones. This is the pentagon with the extra one with no buffer zone. So this is you can see that the cyclones are interacting and will merge. So you're looking up at the south pole of Jupiter here. So these are lines of latitude. So if you have no buffer zone, then the cyclones will essentially merge into one larger, more rapidly spinning cyclone. But if you have these buffer zones, which are rotating in the opposite direction, which are depicted here in white, you have the stable pentagon, and then this extra cyclone that kind of wiggles its way in. One caveat to this model is that this model is 2-dimensional, and so it doesn't take into account the vertical winds up and down within Jupiter's atmosphere, which almost certainly has a large effect. But this is one hypothesis as to how you can get a long-lived pentagon on the poles. Pentagon of, or now I guess hexagon of cyclones at the poles of Jupiter. Okay, the second headline is there have been surveys of disks around white dwarf stars. And so I'm not going to pretend I can pronounce this last name. Gansky et al. Examined the Sloan Digital Sky Survey for 7,000 white dwarf stars, and they only found one white dwarf star out of 7,000 that had what they determined to be a gas disk from an exoplanet that had been eaten or cannibalized. And so they are now going to look at the European Space Agency's Gaia survey, which contains more than 260,000 white dwarf observations, to see if they can find more of these cases. And so they're looking for something kind of special. So it's long been hypothesized that white dwarfs will cannibalize the planets that are orbiting around them. And we have observed, sorry. There we go. We have observed, I hadn't, they have observed disks of debris falling into the white dwarf, but they're almost always of rocky composition. And so this is the first time that we've observed a gas disk. So they observed this 19th magnitude white dwarf, whose name is a jumble of letters, using the X-Shooter spectrograph on the European Southern Observatory Very Large Telescope. This particular white dwarf is 1,500 light years away in the constellation of Cancer. Its surface temperature is very hot, 28,000 Kelvin, and so it emits most strongly in the UV, and this will be important in a little bit. And so they also observed, using spectroscopy, that it has a circumstellar disk made of gas that is about 20 million kilometers across, and it consists of hydrogen, oxygen, and sulfur. They note that these are the same elements that would be present in the deeper levels of the atmosphere of an icy giant planet like Neptune. And so they also state that the white dwarf is accreting material at an incredible rate of 3,000 tons per second. Okay, so the scenario that they propose is that you have a giant planet that orbits a star, the star goes red giant, there's a white dwarf left over after the planet has died. The UV radiation that comes off of the surface of this white dwarf will blow away the hydrogen of the giant icy planet. So it'll be a comet-like hydrogen tail behind that planet. The oxygen and the sulfur, which are heavier, won't be blown away by the radiation pressure in the same way. And so they'll fall inwards and create an accretion disk around this white dwarf. And so you would expect, or they propose, that you would see a hydrogen tail behind the planet, and then oxygen and sulfur in the disk. Oxygen will emit in red in the inner disk, and sulfur, shown here in blue, will light up the outer disk. And so this is an artist's depiction of what that might look like. So the most plausible origin of the material is an evaporating gas giant, which is in a close orbit around the white dwarf. But this orbit is very, very close, and so it would have been within the red giant phase star when it was in that phase. That was poorly phrased. So at the current distance of that planet, earlier in time, when the white dwarf was a red giant, the planet would have been orbiting inside the star. And that's unlikely. So what they suspect happened is that the ice giant started much further away, and then due to gravitational interactions with other planets, fell inwards and is now orbiting much closer. Okay. Okay, I'll do questions for all three at the end. I took way too long last time, so I'm trying to be mindful. So now, first science results from the Parker probe. So excited. Okay, so this was launched a while ago, and this mission has now made 3 perihelion passes and has come closer to the sun than anything we've ever sent to the sun before. So the first perihelion pass was just over a year ago, the second one was in April, and then the most recent one was this September. So the perihelion, the closest one, was just 24 million kilometers away, so 1.6 astronomical units, or 34 solar radii away. And so at this point, it's made 3 of its planned 24 perihelion passes, so we're still in the early stages of the mission. But it's on a 150-day orbit, so hopefully it'll take us from solar minimum when the sun is nice and kind of quiet and simple, in quotation marks, and then kind of lead us into solar maximum. There are 4 suites of instruments on this spacecraft. Fields investigates very creatively the magnetic field and electric field, as well as some of the radio signals. Sweep, the solar wind electron alphas and protons, is similar to a Faraday cup that's on a lot of other solar wind instruments. And so it measures electrons and ions in the solar wind, so the thermal component of the solar wind. The wide field imager, for solar probe, or WHISPER, images the sun and the corona, so that's just a white light imager. And it takes images when it's close to the sun. And then finally, the Integrated Science Investigation of the Sun, or ISOS, measures really energetic particles, so the ones that have been accelerated by solar flares or coronal mass ejections. So there are kind of 5 main surprising results. And I'll show you the video that NASA put together for it because it's excellent. Can you guys hear that?
Traveling through the sun's blazing hot atmosphere, NASA's Parker Solar Probe has sent back a complex, close-up view of our star. The spacecraft confirmed that our picture of the sun from Earth is deceptively simple. Parker is the closest spacecraft to the sun, meaning we now have never-before-seen details about the solar wind and solar energetic particles. Solar energetic particles are high-energy particles that can endanger both astronauts and satellites in space. The solar wind is the continuous outflow of particles and magnetic field from the sun, both speed out, filling up space, and affecting space weather throughout our solar system. For the first time ever, we were able to go to the source of the solar wind and solar particles. Here are 5 features Parker saw. We've long known that space is full of cosmic dust. We can even see the dust from Earth because it reflects sunlight. Parker saw evidence that the dust stops at an estimated 3.5 million miles from the sun. As the dust gets closer, the sun vaporizes it, creating a dust-free zone surrounding the star. At Earth, it appears that the magnetic field lines flow evenly out from the sun, but Parker saw them behave in a surprising way. The magnetic field lines flip in a whip-like motion, turning 180 degrees around in a matter of seconds. These switchbacks came in clusters and were timed with fast-moving clumps of plasma in the solar wind. Scientists have long wondered if the solar wind is generated as a continuous flow or in spurts. We now see evidence that the solar wind has rough, irregular texture. The plasma within it also seems to lack an orderly sense of direction. Some clumps of solar material fire out into space, while others fall back toward the sun. These clumps may be distorting the magnetic field, causing the switchbacks. They may also be an indicator of what the solar wind looks like in its early stages after its birth on the sun. Parker found a transition point in the solar wind. The corona is the sun's faint, outermost layer that transitions to the solar wind. Before Parker, scientists knew that the corona rotates with the visible surface below it, but they didn't know how or where the solar wind switched to flowing straight by the time it reaches Earth. Parker has finally spotted signs of this transition, and the changeover happened significantly farther out than expected. Although the sun has been very quiet over the first 2 orbits, Parker observed several tiny bursts of solar energetic particles. While these events have been seen before, never ones this small. The fast-moving particles from these modest bursts spread out as they move from the sun, making them undetectable from Earth. Without Parker's front-row seat, he would never know that the sun is regularly producing these small-scale events. Fast-moving particles are a source of dangerous radiation. The more we learn about these eruptions, the better we can protect our technology and astronauts. Parker still has more work to do, but it's already helping us see our star in a whole new light.
Okay. Here are my sources. Take us back to a pretty picture. I'll answer any questions you guys have. four instrument suites. There's fields, so it's a magnetic field and an electric field analyzer, and then a radio antenna. Suite measures electrons and ions, so it's a Faraday cup. And then the wide field imager is, the Whisper is just an imager. And then the integrated science is probably a time of light spectrography. So essentially you're measuring the electromagnetic field, the bulk of the stuff in the solar wind, taking pictures of the solar wind, and then measuring the really energetic, like storm level type particles. Yeah?
Didn't some of the results indicate some insight into why the corona was so much hotter than expected?
Yeah, so the coronal heating problem has been like the bane of solar physicists' existence for a really long time. And so we've suspected there are kind of two camps. And so one camp is alphanic turbulence. And so alphane waves are waves on the magnetic field. And so if you get a bunch of these waves at different wavelengths and frequencies will interact with a turbulent cascade, and that will heat up the corona. Or you can get microflares, and so you get a lot of little reconnection happening in the solar carpet of the magnetic field, kind of in the chromosphere, and then that will accelerate particles, which will then collide and heat things up. And so there is evidence for both of those processes happening, but the switchbacks in particular really tell us that there are some really large-scale alphanic waves happening, and they're happening much further up than we thought, which will tell us were hints that they're also present in larger numbers than we thought further down. And so these switchbacks might be evidence that the alphanic waves is really what's doing a lot of the heating. Yeah, really interesting. So the closer we get, the better it will be for trying to answer that question. Yeah.
Said that there were 5 cyclones and the 6 flying, but when you saw circles, there's 7.
Yeah, sorry, for the cyclones, so there are 5. So in the South Pole, here, there are 5, this is, okay, these are all, okay, this is the original image. So there's one central one, and then 5 around. And so they called it the Pentagon, but there was actually 6 of them. And then now, there's a 6th one that's been added, but so it's a hexagonal, like outer shape, and then one large central cyclone in the middle. Yeah?
I read not too long ago that the sun is a dwarf star. Is that true, and what makes it a dwarf star?
The sun is a G2 type star. It's pretty average, so it's not a dwarf star. It's a pretty middle of the road in sequence star. Yeah. Oh, just a stretch. Yes, over here.
Back on your story about networks, I'm just wanting to understand that as far as the theory about having a large gas giant that sort of gets behind the star or sort of stirred up by radiation. I'm just trying to understand, so if the gas giant has enough orbital velocity kind of for all that's happening, what would cause the sulfur actually start to fall? Like, is there something that slows it down that it starts to approach the white dwarf?
Once a planet is already close, or I'm not sure I understand
Oh, sorry.
the question. Sorry.
I understood the part about the ultraviolet radiation and then so the lighter elements, so hydrogen, helium, that gets blown out, so that makes sense. It's a little bit of a comet. So the heavier elements and the sulfur, I'm just trying to understand why it would, it sounded like it would slow down in its orbit and would decline, so that actually some of those heavier elements get closer to the white dwarf. But I'm just trying to understand, is it already
there's like a particular drag that happens where, oh,
Yeah,
no, shoot.
Isn't it tidal influences as well?
Not for individual particles, but you get it in the solar system where certain, oh, shoot. Yeah, it happens with heavier elements in our solar system too, and so I can't remember, but there's, I don't have the answer. Let me look it up and I'll find you at the break. Sorry, I don't know what it is.
No problem, thank you.
Okay, that was at the tip of my tongue, and I didn't want to call you out just in case, but thank you. I think it's it, but I'm not sure. Okay, yeah, I think it's the pointing ground. It's not great. Sorry. Thank you. Anything else?
What's the mission like for the solar?
For the Parker probe, I think it should go to 2020. Oh, it's got 2,450-day orbits.
And what's the new mass?
Oh, so the, oh, shoot.
What's the closest?
I think the closest it will get, so the current perihelion is 0.16 AU, and I think it's going into 0.08, I think. So it should get a little bit closer than this. Yeah. So it's highly elliptical, and so then it does a couple Venus flybys, and slows down and follows in. Okay. All right, thank you.
Take a short recess. We'll be back at 9 o'clock with our main presentation. We have some, of course, refreshments and some food for you guys.
Could be at our place, it could be at
Speak up. Can't hear you.
Jim, turn up your hearing aid.
Sure, yeah. All right, it's done that.
Yeah, that's nice, I think I can work with that. We should be able to see anything that's thrown at me.
I don't think your mic's on, Jared.
Yeah, that's right. We're going to start off, I had a little chat with Ian earlier too. I've got a subtitle here that I think I should actually give credit to. Apparently this summation of Kepler was one given by Carl Sagan in his series Cosmos. And since I came at it independently of him and thought that this was my two best summaries of what Kepler's about, I decided I don't need to give Carl any more credit than Scott. Kepler is the third of my talks on the scientific revolution, otherwise known as the Copernican revolution. And the reason, the motivation for all of this stems from, oddly enough, the mandate for the Royal Astronomical Society. On our national email list and on many other places, what happens is we start doing this. We're promoting and increasing the knowledge in astronomy. And sometimes when we do that, we kind of use science as a bit of a sledgehammer on things. And as you see, these first two statements are straight off of our national list mandate, and talking about the RASC values discovery through the scientific method. And yeah, the scientific method is what we're using as our sledgehammer here to correct, to cajole, to bash, to in some ways intimidate all sorts of other enterprises. And sometimes I get a bit bothered and disturbed by the way in which we're doing this. I've had a fair bit of experience dealing with the scientific method from a sort of outside viewpoint, so I always got a little bit
nervous about when I saw it being used, especially when I thought it was being used inappropriately. And the scientific method is best encapsulated by its first example, the scientific revolution, as it's called, or more specifically, the Copernican revolution. And in my first two talks, we talked about the first two characters in this story. And essentially, we came up with the idea that the real issue here is not as clear as what we thought it should be. And we were sort of left with this little diagram here saying, out of all the reasons why this revolution took place, the aesthetics of these two diagrams is probably the most convincing bit of argument that we have for the entire story. One is nice and neat, the other is all messy as all heck. So, but we're going to go further into that issue with tonight's story. But just to give you a background, in case you missed the first two sections of this, we've got a story of the scientific revolution. The story of the beginning of science being used to describe astronomy. And it starts with our boy Copernicus here, who goes from the old Ptolemaic system of, a fixed Earth and all the planets and everything going around the Earth, to one in which the sun is at the center of the system, and the Earth now is free to move in orbit. With Copernicus, the way they tell the story is Copernicus came at a time when astronomy was in great dire straits. It wasn't doing very good. It had problems. The models weren't working. And he came along with his new, better, faster, simpler system and was able to win over the hearts and minds of the dispassionate, the objective thinkers, and won them over to his view. Tycho Brahe, which I talked about last time, was the great data collector who amassed all the information that was needed to actually prove the system. He handed off that information to the very capable hands of tonight's guest star, Johannes Kepler, who straightened out all the problems of the Copernican system. Along comes Galileo, who invents, slashes, just makes, whatever you want to talk about there. And Galileo goes through to find all this information that proves that the Copernican system is superior to the old Ptolemaic system. Then along comes Newton, who says, okay, all of what you've been doing here sounds and looks pretty great, but it needs a theoretical underpinning. And he comes up with his theory of gravitation, which binds the whole thing together, and Bob's your uncle, and the revolution is over at this point. That's the textbook story that we get on this. Now, I'm going to give you just a bit more of a timeline that's more specific to tonight's talk. Kepler is our main man here, and here his dates show how he overlaps with many of the other major characters in this story. Copernicus, of course, is long dead at this point. Tycho Brahe is alive for about half of Kepler's life, and Newton, the final story here, is beyond our purvey tonight. But Galileo figures prominently in this, as his life overlaps that of Kepler. A couple of important things to include here. I put this one in here talking about 1609. That's when telescopes started to be pointed at the sky. Well, actually not really, but we go with that story on that. There's several other events that we should think about here. There was astronomical events at this period of time that were very prominent in helping to shape the attitudes of the time. The comet of 1577, which we'll talk about later, is one of the events. There was, at this time, in the lifetime of both, well, if you just go a little bit back into Tycho Brahe and a little bit into Kepler's life, they had two supernovas that they could see. They were naked eye visible things in the daytime. They were that bright. We in the Northern Hemisphere haven't seen anything like that since. So it's been like 400 years counting before we're going to be able to see something like this. And so there was these very monumental events. The comets they had, in the year 1618, we're right about in here, three naked eye comets in 1 year for them to look at. And one of them was an absolute stunner. Crossed half the sky. It was half the sky across. Just beautiful stuff. So these guys were kind of fortunate. They had some really good stuff going for them at the point. But let's get to our main man here, Johannes Kepler. There's his date. Here's the usual description of him. He was a Copernican, so he was one of the people, one of the good guys in our story here. And yeah, he practiced astrology, but you know, he held his nose while he was doing it. He didn't really want to do it. You know, they make him into the nicest guy that they possibly can in this way. Nowadays, if I was to be giving this talk 20 years ago, it wouldn't be like this at all. Because so much of the literature on Kepler has come out in the last 20 years showing the dark side of Kepler. Okay, this guy has got another side to him that we really didn't have in the literature up until now. So it's kind of interesting to see how this works out. Now, they acknowledged this before, but now this is taking center stage in the formulation of Kepler's thought. One of his accomplishments was he was the imperial mathematician for the Holy Roman Empire. And he held that position for over a decade, where he did such things as was calculating the birth date of Jesus Christ. And he found out it was like 5 BC or something like that, so 4 or 5 BC calculations. Essentially what he was doing was he was working on calendars and calendar reform and going back through everything that got messed up in calendars and realizing, whoa, we got this all messed up. So, he's of course famous for his 3 laws of planetary motion. This is what we take forward out of Kepler's contributions to the whole scientific revolution. And that's drawn out from the rest of the story and said, okay, here's the good stuff that Kepler was doing, and this is what we want to take from here moving forward. So we get this really sort of distorted view of everything else he was doing. Of course, the big thing that he was famous for was finally abandoning the idea of uniform circular motion. The only physics that we had handed down from the big A, Aristotle. Without the idea of uniform circular motion, we got nothing as far as a physical explanation for why something would keep moving forever. The only thing that these ancients could conceive of as being essentially a perpetual motion machine was the idea of spherical uniform motion. So he got rid of that, and this was a source of lots of problems, as we shall see. But the man did so much more than that. His work in optics alone would have made him a famous character. He did work with, I put down the word camera here, but of course what I should have written was camera obscura, because he was working with the little pinhole cameras. And it was working with pinhole cameras that he recognized that you had all of these ways of tracing light with what he called pencils of light, which we now call, ray tracing diagrams in optics now. So he came up with a lot of that. He was the one that brought forth the understanding and the description of nearsighted and farsightedness, so that you could make better glasses for different people. And he came up with his own telescope, which was way better than Galileo's. So we're going to get into that a bit too. He also created the Rudolphine tables, which were, throughout the 1600s, the most accurate description of what was happening in the sky. It was good enough that they were still using it over 100 years later. It really was a very tour de force work as far as getting out a very accurate description of the motions of planets. He also wrote the first, that it's sort of acknowledged now, the first science fiction novel of all time, called Somnia. It was a story about this guy who went off to study with an astronomer for a bit, wished he could go to the moon. His suspect witchcraft mother was able to summon up a demon that got him to the moon. And then the rest of the story is a description of what it'd be like to do astronomy from the moon. What would you see, what would move, what wouldn't. And so we've got a real science account in a fictional environment here. So this is where he gives the credit as writing the first science fiction novel. He even left us with catchphrases. The most prominent one being, "Don't throw out the baby with the bathwater." This is the first known use of that phrase. So this guy did a lot, and he did it in a very arduous time. I've got this down at the end here because this is what we're going to try and decide here. Is Kepler the great scientific mind that some people claim he is? Like some people want to say, don't call this the Copernican revolution, call it the Keplerian revolution. He's the guy who did stuff that was radically different. He got rid of all that circular stuff that was going nowhere for 2,000 years. Kepler was the guy who actually brought back in a physical account of his model rather than just worrying about the kinematics. You know, never mind the forces here, we're just going to worry about where things are. And he went further than that. He brought the physics side, an analysis of what was pushing this stuff, what was forcing it, the forces involved. And by doing that, he's given this claim as being the first modern astrophysicist. And so by that description, well, yeah, he's got to be this great scientist. On the other side of the coin is this guy had a very peculiar, very definite bent on how he was doing things and what he thought he was doing. And it doesn't sound all that scientific, as we'll see. So what we're learning now is the way in which the early accounts we've had of Kepler in that very simplistic textbook-style story of the Copernican revolution just doesn't do the man or the whole subject justice. This is also a tale of triumph over adversity. This guy had it tough. It was a very discouraging existence that he had. He was born near Stuttgart, Germany, to a poor family. The only claim to fame was his grandfather was the mayor of some town. His dad was apparently abusive and a drunk and a mercenary soldier who left the family early and left him and his mother in kind of dire straits. He also had brothers and sisters. He was born premature, 2 months premature back then, which was almost a death sentence. He suffered smallpox at a young age that left his hands crippled and left him with bad eyesight that he had for the rest of his life. So this guy started off really bad to begin with. He was plagued with sores and pains and other gastrointestinal problems his entire life. He also had to deal with the fact that he was in this part of Germany at this time, so the Protestant Reformation is going forward, and he considered himself a very good Protestant, but his church didn't. They thought that his peculiar version of Protestantism was, well, you're almost a Calvinist already, so they wanted to just back away from this guy entirely. There was a bit of a problem here in the way in which he was picking and choosing the way he thought Protestantism should work. And this caused him no end of grief later on as well. He had to deal with various plagues, for instance, and this ties in with the family tragedies here. Of course, families back then lost a lot of people. The infant mortality rate was very high. And such was the case with Kepler's family as well. Almost every biography I read, you read at some point, oh, again, and then one of his children died, and another one died, and it's just terrible circumstances for the way in which this guy had to deal with things. His wife was also taken by Hungarian spotted fever. His first wife, I should say. And there's so many other trials and tribulations dealing with these various plagues. For instance, he finally gets to the capital of the Holy Roman Empire, which was Prague in Czech Republic now. And he finally gets there, only to find out they're vacating the city. Another plague is moving through. So, okay, everybody's got to go out, and they got to just drop what they're doing. And if you were rich enough to be able to do this, then you could leave the city and wait till the plague ran its course, and then you could move back in again and business as usual. So there's all these issues to deal with at this point. Oh, and then there was his mother. I guess she did her best. I mean, she was, by best description, she was a herbalist. She was a sort of a naturopath who's made most of her living selling, you know, regular remedies, cures for what ails you out there. And to be doing that kind of thing back during this period of time, you were always treading very closely to being considered a heretic, and worse yet, being condemned as a witch. And that's exactly what happened to Kepler's mother. And Kepler, who didn't have that great an opinion of her to begin with, I think he was racked by guilt. Because in that book that he wrote, the science fiction book Somnium, he told this story about this bright young lad who wanted to go off and spend his time with Tycho doing astronomy, except that his witch mother summoned up a demon who transported him to the moon. Now, a few years after that story comes out, Kepler's mother and 7 other women were locked up on charges of witchcraft. And she spent 5 years in jail, and Kepler had to drop everything he was doing to mount a legal defense. And he eventually got her out, but she was exiled from the local region, etc. So, again, trials and tribulations that the guy had to do for it. And then he had his professional enemies, and we're going to look a little closer at that because that reveals a lot of the story of the scientific argument that we hope to get at. You're an astronomy bunch, so I thought we'd bring out this little tidbit here from his work. Here is the design of a Galilean telescope. I don't know if you've tried to look through a replica of a Galilean telescope. They're awful. They're just terrible. Matter of fact, a few years back, when Scott Young had that replica model, he brought it to a meeting here. We were just out in this hallway trying to use this telescope. What a nightmare. This thing had a field of view that was so narrow. There's a tower over by the university center there. It's a tower. You swing across to it, you go up it, and you should see the top of the tower. It took me 15 minutes and I couldn't do it. This thing was horrible. Its field of view was so narrow, the focus seemed to never be where you wanted it. It's an absolute nightmare of a telescope to use. With Kepler, once he understood a little bit about optics, said, well, yeah, that thing's a piece of junk, and thought that he could do a better job about it. So he designed his own version of the telescope. He understood about real focal points and virtual focal points. He's the one that actually gave us those terms for the way in which we understand telescopes now. And his telescope design is what we also call an astronomical telescope. It's the basic design of all of our refractors to this day. Yeah, we put in more mirrors up front and got more complicated eyepieces and put in our fluorite glass and all these other things. But basically, Kepler's design is still being followed. We try and bring to focus something after the focal point of the objective lens. So we're still in some ways using Keplerian refractors. Nobody, unless you've got a set of opera glasses, ever looks through a Galilean telescope. Those things are just too difficult to work with at the best of times. Over here is Kepler's drawings of eyeballs. Judy would have loved him. I mean, he was cutting things open, he was taking these things apart, he showed how the lenses worked, he understood that the images on the back of our eyes were upside down from the optics involved in our eyeballs. So he had all this stuff sorted out. And this also helped him, along with this, tracing the pencils of the light through, to work with the optics that gave us this better telescope. And why is it better? Well, first and foremost, it has a great field of view. Galileo's telescope was the first one was 20 power, the second one was like 30 power. Apparently, one Galilean telescope was made for 50 power. And it had such a pathetically small point of view, it was virtually unusable. Maybe you could get half a crater on the moon in there and that would be it. It's just terrible. Part of the problem there is that as you increase the magnification, that field of view just shrunk to nothing in no time. With Kepler's design, it's the kind of telescope we're used to now. Yeah, you can pump the magnification up to 100, 150, and you still got a decent-sized image to work with there. So the Keplerian design telescope quickly took over. And almost everyone in the later part, well, from the mid to later parts of the 1600s, they were always using Keplerian design telescopes. Nobody bothered making anything like Galileo had. This is one of the wood cuttings that went into a printing of one of his books on this. And it's just a map of the world. And just to show you the versatility of the man here and what he was doing. All this fuzziness here, this is all labels. The entire globe is something that he has, gone through and labeled as far as concerned. So of course I went up here, here's Hudson's Bay, and I looked down here, and this place used to be called New South Wales? Who'd have known? Anyway, that's the way it was referred to at some point in our existence. But yeah, just the details of his map in the early 1600s is when this map of his was included in with his big atlas on ephemerite. In 1577, the Great Comet, otherwise known as Tycho's Comet, because Tycho was the guy doing all the plotting and research into this comet's concern. Kepler was 6 years old. His mother took him to a hilltop to show him the comet. This must have really impressed the young lad immensely at this point. He was able to be allowed to stay up for lunar eclipses after that, and so his interest in astronomy formed very early. He was also being schooled to become a clergyman, and so he was already starting to organize his religious beliefs, but they were tainted by these two Philistines here, Plato and Pythagoras. And Plato you might know about, who was sort of this idea concerned with sort of the absolute forms behind our ugly, imperfect reality. And Pythagoras, you might remember from the Pythagorean theorem, the idea of, the squares of each side added together equals the square of the hypotenuse. There was a classic example of Pythagoras' main theme that the universe and the world could be understood through mathematical equations. And in some cases, it was more than just understood. It was a way to get at the force, the structure of our universe that mathematics imposed upon this stuff. And so you've got a very curious combination of attitudes and beliefs in young Kepler. This quote of his at the just included at the end here is from much later on in his life, but I think it sums up pretty much everything that he was doing from start to finish. I also ask you, my friends, that you do not condemn me to the treadmill of mathematical calculations. Allow me time for a philosophical, scientific speculation, my only delight. Because by the time this guy graduated, straight A student, matter of fact, there's still some records at the Tübingen University that you can look up saying, whoa, this guy's good. He's going to do something really great And so they were, anticipating the genius that was going to be Kepler. And yet, what did they do? They sent him off to Graz in Austria there to teach mathematics. And he turned out to be a horrible teacher. First year he had 6 students. Second year he had none. Nobody wanted lectures from this guy. He would all of a sudden in the middle, and he'd go off and just work on something and let the students hanging. And the guy was just the worst teacher you could ever imagine. But, oh well, had to have it all. Now, the interesting thing that sort of tempers all of Kepler's scientific endeavors is his relationship to astrology. First of all, a prognosticum is just a list of predictions for a coming year. Astrologers are doing this all the time. I'm sure they're coming out with their predictions for 2020 now or whatever. His predictions for 1595 were really good. He said 3 things in particular, especially, he just got to Graz in Austria there, and he came up with 3 great predictions here, he said. First of all, we're going to have trouble with the Turks. The Turks are going to be uprising, and there's going to be invasion problems from the Turks. The next thing is, it's going to be a really nasty cold winter. So see, Jay, these guys actually, astrology, can help you guys here a bit.
I'm working on it.
And the third thing was, there's going to be a peasant uprising. And all 3 of these things came true, and they're like, oh boy, this guy's good. And so his position from then on was, okay, get my astrological chart drawn up. And so he spent so much of his time doing these mind-numbingly silly calculations all the time, right through. And so he was condemned to his worst fear of just being this number cruncher, grinding out stupid astrological predictions all the time. Now, I say stupid because that's me talking on top of this here. Kepler's position on this was a very uneven thing. First of all, he hated all the bold predictions that astrologers ever made. But he couldn't deny that there was some sort of connection between everything in the universe. And that, as we're going to see in some of his other books, there's an underlying current of everything being a law-like motion, a trend of the universe that we should be able to determine. You don't need to have a book to know God. You could just find God's message in nature. It was written out there if you were clever enough to see it. And so this was the mandate of Kepler more than anything. An interesting aspect of education at this time, astrology and astronomy were considered a couple of liberal arts together. And you can see the way in which they went together. Of course, you can't do your astrology without some astronomy to use as data. So you had to have both of those things in. Physics, the description of what sort of, forces, momentums, everything that went on to cause all of this, that's not the fine arts, that's not the liberal arts here, that's going to be something totally different. You leave that to the natural philosophers, as scientists were called back then. That's not part of what astronomy and astrology are all about. So there's a difference here between talking about physics, which is what he wanted to reintroduce, and the stuff that was concerning him. He regarded astrology as kind of being like medicine. You win some, you lose some, you're sort of generally going at the subject. He considered astrologers to be like chickens scratching in dung. Every so often you'd come across a kernel, a grain of something that was useful and something that resonated, made you think, aha, there really is something to this here. That was sort of his attitude. He was quite willing to say, yeah, at the time of your birth, or actually if you want to talk about time of conception, but that's a lot trickier to figure out. Anyways, you wanted to talk about alignment of the universe at the time you were born. He says this is going to be some sort of general influence on you, but not to the idea that, I can tell you what's going to happen to you next Tuesday. No, that's not the way this stuff works. He got from Aristotle this idea of anima. He wanted to explain three things. He wanted to know why the universe is the size and number of things that it is, and he wanted to know how it moved. And when you get rid of, as we shall see, he abandons the idea of perfect circular motion as our explanation, as our physical account of what makes things go, he has to introduce his own ideas. And he talks about this idea of anima, or a more complete term, anima motrix, the moving force. And the people who talked this way came at this naturally enough. They came upon this by the idea of what moves? Well, living creatures move. Creatures with, that élan vital, that kind of that life spirit, or some kind of soul in them. That's what moved things. And that's what he was hoping that he was going to be able to help describe here. The universe, as it was unfolding, is exhibiting great harmony. And he just doesn't mean that as a metaphor. No, he really means this in terms of the music of the spheres. And he plotted out the musical notes that he thought each planet would make. So he went through a whole very complex way in which he thought he could mathematically describe harmonies in the universe. And of course, these two jokers in the background were always figuring prominently with such statements as this. This is a statement of Kepler's, by the way, but it kind of gets at these ideas of Pythagoras and Plato. Geometry existed before creation. In other words, when God created things, he had to do it along the lines of what geometry permits. Somehow this was a fundamental aspect, a structure to nature that you had to follow. There was no other way of doing it. Oh, and by the way, this stuff over here on the side, if you're interested, the Kepler College has its superb astrology software available. I think they're into version 7.0, so it's getting better. And if you're really dedicated to the cause, here is an example of the certificate from the Kepler College here. You probably can't read this, but it says, has successfully completed at least 140 weeks training and at least 1,200 coursework hours and all additional requirements for the professional diploma in astrology, completed December 2017. Okay, so these guys must be good. To spend that many hours trying to learn astrology, they must be at some point saying, well, there is something more here to learn. So the lesson maybe to take out of this is, not all degrees at universities might be of similar value. When people think of Kepler, they almost immediately think of Tycho as well. I mean, some of the ways in which the scientific revolution is described is in terms of how these two were almost like a tag team. They were a partnership here where Brahe was allowed to give you the data. He was the great data bank, the guy who collected all the information. And he handed it over to the mathematician genius here. And they were able to cooperate, work forward, and come up with the revised version of Copernicism that we have today. But the truth of this is far from that. First of all, there's 25 years difference in the age of these two guys, and they really didn't see eye to eye on any of it. Even though their lives overlapped for 30 years, for 30 years on this planet, both of them were around, it's really only about a year that the actual cooperation between the two of them happened. There was some letters beforehand and communications between them, but no, what happened here was a very brief actual encounter. And most of that year, they spent fighting. There's accounts of, Kepler blowing up, running away from Prague, coming back a few weeks later saying, I'm sorry, and going through the whole deal. So this was a very tortured, strange relationship. Tycho Brahe was a bit of a nasty boss to work for, and he kept his data hidden, he kept it locked up, he wouldn't let Kepler have any more than he thought he should. It got off to a really bad start, because Tycho was in a big argument over priority with one of his rivals, a fellow by the name of Nicholas Reimers Bayer, otherwise known as Ursus. And Kepler, in his youth, wrote a letter saying, oh, Ursus, you're just the greatest mathematician going, and I think everything that you did was just the greatest. I've learned all my mathematics from you, and blah, blah, blah. He's really kissing up. And Tycho heard about this. Or worse yet, Kepler's real mathematics teacher heard about it and said, what? What am I, chopped liver here kind of thing? Really bad scene between Kepler at this point and all the rest of the people that he ended up working with. It's a whole big story. I won't get into any more of it than that, except to say that Kepler, to apologize to Tycho, spent almost a whole year writing a defense of Tycho against Ursus. So, I mean, the extent to which some of these little squabbles took on huge proportions is just stunning. The two of them had incredible professional differences. Their approach to science was a little bit different. Both of them liked the idea. They were both scientists in that sense, that they wanted to look at data and let the data decide the issues. But between the two of them, they couldn't be any more different. And personalities-wise, they weren't like each other either. You've got a case where Brahe was, a loud, boisterous, rich, aristocratic Dane, versus this quiet, shy German character here who really didn't like any of this boisterousness that he got from Tycho, and they never really saw eye to eye on most of it. And he was so frustrated with Tycho because he said, hey, you hired me to do the math on your data and you won't even show me the data. And you know the story about Tycho Brahe. He got into a fight over mathematics and lost his nose and all of that kind of stuff. And it's like, okay, in 1908, I think it was, they dug up Tycho's tomb and exhumed the body and checked, wow, was that really a gold nose that he was wearing kind of thing? Turned out it was bronze, so no great discovery there. But when they did some tests on him there, they discovered an incredible amount of, was it mercury or arsenic in the hair samples they took. And yeah, anyways, they thought, uh-oh, he was murdered. And who had more motivation than Kepler? So this became this great scientific murder mystery about him. And hey, we dug him up once in 2010. So about 9 years ago, actually, in November of 2010, they dug him up again and did more samples and testing on poor old Tycho's carcass, and found out, yeah, you know what, maybe not. Doesn't look like the toxicity that he had to deal with was all that great. So remember, this guy was into doing stuff with alchemy as well, so he was exposed to a lot of bad chemicals on his own. He didn't need to be murdered over this. So even though you can go online and find all kinds of stuff about the conspiracy here and the murder stuff, you can pretty much ignore it. There's other characters to sort of put in the background story here. Here is his actual mathematics teacher from Tübingen, the university there where he went to. And this guy was a closet Copernican. He liked Copernicus, but he didn't want to dare come out in support of it. He did teach it to Kepler, and Kepler took to it immediately. and uncritically. One thing to understand about Kepler is he wasn't a good scientist. He didn't weigh the evidence and decide, okay, this is the more correct theory. He just loved it from the get-go. And he was a crusader for a Copernican version of the universe all of his life. Michael Maestlin was very helpful to Kepler in the beginning, but once Kepler started publishing enough works with all of these very controversial ideas, Maestlin backs off and says, yeah, you know what, I think that's a little too much for me to help you with. And yeah, so you lost your job again and you're looking for another university. Yeah, I can't help you with that either. So there was so many times in the early years where Maestlin was key to helping Kepler. Later years, it's like he just backed off entirely. The biggest problem was he didn't like this idea of Kepler violating this boundary. He was trying to bring physics back in with astronomy, and it's like, no, Johannes, that's not what we do. Don't try and do this. It's a mess. You're not going to be liked. It's not going to be acceptable, and it's just plain crazy. So don't bother trying to do it. The other main character in the background here is the Emperor Rudolph II of the Holy Roman Empire, based at this point in Prague. He actually was the man who brought all of these characters together. The first of the three to be imperial mathematician was Ursus, as I had mentioned earlier. Then he hired Tycho. When Tycho died, he gave the job to Kepler. And he was also quite a hands-on ruler. He went around there lots of time to make sure, so, how are you doing? And what are you doing, kind of thing. So he was quite instrumental, saying, so, what do you need now, kind of deal. So he was a relatively useful benefactor to the whole scientific enterprise. 1596 is the first publication of Kepler. And it's this wild, exuberant, bold publication that you might expect from a young scholar. Comes out saying, yeah, Copernican theory is right, and this is the first time in print someone's come out and endorsed it. And this is like 53 years after Copernicus published. After 53 years, after half a century, someone finally came out and said, yeah, good work. I mean, they said it in the background, but nobody published about it. He also sent a copy of this work to Galileo, and we'll talk a bit about that later too. But I just wanted to get an idea of some of the stuff that he had in this work. Geometry was the structure of the universe, and he came across what he thought was this brilliant insight, that if you take the Platonic solids, these polygons that were regular in shape, and if you combine them in the right order, they defined the ratio, the spheres that you put. So here's a sphere inside of the tetrahedron. Here is a sphere inside the cube. And here is a sphere on the other side. So this would be Saturn, this would be Jupiter, this is Mars, and then you could go inwards and inwards, and so on. And by using all the regular solids of the past, you could define the relative distances of the planets, which they knew the relative distance. And he said, and the number of these, which is very limited to this 5, I mean, you can get quirky things if you broke some rules, but this defined the number of planets. The number of planets had to be what they were because this is how many of these you had to deal with it. And you should be squirming a bit at this point because this is starting to sound like some kind of bizarre numerology. It's not on tack for that. And his idea of the sun at the center and also as a prime mover. In some ways it was the sun that was going to move the whole thing around. It was no longer the sphere on the outside that was perfectly moving around that trickled down in its motion. This happened on the inside forward. Then he came across the work of a couple of people working on magnets, William Gilbert being the most prominent one, because because he's the one that proved that the entire Earth is a magnetic field. And they started to understand and explain the forces involved in magnets and realized, okay, and now we know that the Earth is a magnet. That probably means that all the other bodies are magnets as well. And they already had evidence of a rotating sun, so its magnetic field would be sweeping out around this way, and wow, the sun rotates in the right direction to move planets around. He thought he was finally grasping at the idea of the physical cause of the motions of all the planets here now. And he farted around with all the details of it all here. He also was claiming this idea that the magnetic attraction extended from the Earth to the Moon, which meant that, yeah, the spinning of the Earth is what was throwing the Moon around. And this has all got a certain plausibility to it, and it's like, it's not totally harebrained out there, but it's like, most of the people who he was trying to convince were like, whoa, like, just don't go there, because this stuff is just a little too crazy for us to even bother with. And we certainly don't like your new term for what you think you're doing here, which we now sort of call astrophysics instead. Kepler also sent a copy of his first book to Galileo, and they had a very odd relationship over their lifetimes, which overlapped a fair amount. But we'll just take a look at this. This is Kepler's remarks after Galileo had written back saying, oh, thank you for the book. Just to let you know, I too am a Copernican, and I have been for a long time, probably longer than you. And, you know, so there was this kind of one-upmanship between the two of them as who was the Copernican longer or whatever. And Galileo, you know, came out saying things like, okay, apparently Galileo even came out and said, you know what, I've only read the intro to your book. I'll get at the rest of it sometime later, but I want to thank you for coming out as being this supporter of Copernicanism, and we can take it forward from there. And Kepler replies to him that the Earth moves can no longer be considered something new. Would it not be better to pull the wagon to its goal by our joint efforts? So he says, you know, we should team up and finally, you know, bring forward Copernicanism here instead of you hiding in the shadows, Galileo, like you have been. So he said, be of good cheer, Galileo, and come out publicly. If I judge correctly, there are only a few of the distinguished mathematicians of Europe who would part company with us. The first thing they get out of this is note who he's worrying about. They're not worrying about the church. They're not worrying about public opinions. This is still a professional debate for these people. They're worrying about the other mathematicians and the other scientists and philosophers of the time. Galileo replies to all this, well, what do you say to the leading philosophers of the faculty here who have never consented to look at planets, nor moon, nor telescope? People of this sort think that philosophy is a kind of a book, and that the truth is to be sought not in the universe, not in nature, but, and I use their own words, by comparing texts. Galileo here is worried about what's called scholasticism. He's worried about this idea that all these people want to do is start having a legal debate over ancient authorities. And nobody wants to actually look at the damn stuff. And this was Galileo's reluctance and reticence through all this time. Whereas Kepler said, look, we're after God's story here. We don't have to worry about this. We can go off and do this stuff, and we're going to win this battle. Kepler had so many productive years after the death of Tycho in 1601. Here's the cover of two of the big books on this, Astronomia Nova, where he brings out his first two laws of motion, and Harmonici Mundi, where he brings out the third law. Or actually, he didn't bring it out, it's buried in the book, and you try and find it. And here are Kepler's three laws. We've got the first law that says, planets don't move in circles, they move in ellipses, with the sun at one focus, and the other focus just being empty. The way you draw an ellipse, of course, is you take a string, with it tacked down at either end and just draw around. That's where you can draw an ellipse. And the definition of it is that this point on this circle has to add to a particular amount from each focus. So you're always adding this amount to this amount. So move the two foci closer together, you'll get something closer to a circle. You move them further apart, you get more and more elongated ellipses. So you can do a lot of things with ellipses that you couldn't do with all the deference and epicycles and all the rest of that stuff. The second law of motion is the one I think that really resonated with Kepler the most. In this, he finally figured out that planets don't travel at the same speed. When they're closer to the sun, they move quicker. When they're further away from the sun, they move slower. And the way in which you figure this out is to worry about the time interval and how much area is being swept out by a line from the sun to the planet. So when it's close to the sun, it sweeps through a larger angular distance, so this angle is greater than this angle. But this area is always the same if the time interval is the same. If this is, 30 days, this is also 30 days, and this is also 30 days, these three areas are going to equal. He finally found his constant. He finally found one of those secret rules that were hidden of God's structural plan for the universe. His third law of motion, buried in the other book, Harmonies of the World, Harmonici Mundi, talks about the relationship between the period of an orbit and the distance from the sun, or the mean distance from the sun. This is where we get this from. This is the minor axis, this is the major axis. You take half of this and you cube that, it will equal the period squared. So you had a way of finally working with all this stuff. It didn't matter if the orbit was extremely elliptical or rather circular. If that semi-major axis was that distance, it took the same amount of time to go around. So we had a real handle here on how to be able to even predict what would happen to objects that we found later. If you found one with a certain period, you would know its distance from the sun. If you found one with a certain distance from the sun, you would know its period. So you had a real predictive bit of information with this third law of planetary motion that was incredibly useful to astronomers later on. And I wish Gail would just come back and do those wonderful constellation studies that she would bring out before. Because if she could have done the one on Hercules before this talk tonight, I wouldn't have to go through this next part. All I have to do is tell you, so please come back and do those again. I love those. We've got a situation where, in the myths of Hercules, he had a whole bunch of tasks to do. One of the tasks was he had to clean up the Augean stables, this huge ancient feedlot full of sheep and cattle with more dung than you've ever seen. And Hercules had to clean out the stables in a day. To do this, he knocked a couple of holes in the walls, diverted a couple of rivers, and flushed the whole thing away. So the hero had accomplished his goal. The late Renaissance period used that term, the task of the Augean stables, as a metaphor for a really big, difficult task that was impossible to do. So that gets us to the next argument between Tycho's #1 student, his #1 apprentice, Longomontanus, a Dane whose real name is Kristen Sorensen, but he was from Lombard, and when you Latinize the names, you end up with Longomontanus, blah, blah, blah. Anyways, he and Kepler got into a fight, because once Tycho died, Kepler got the data. And Kepler started working with all this. He wanted to finally figure out the problem of the orbit of Mars. And it came out that it was just a really difficult, long task. And Longo over here said, you know what, you know, I should have had that data, that should have been my stuff, and look what's happened here. Although you submerged in the shit in the Augean stable of old, you promised your labor in cleansing them anew, and even triumph, as if we should recognize you as Hercules reborn. But certainly no one does. I seriously doubt that such things can even be presented by you. However, I'm concerned lest the sordid insolence of yours defile the excellent opinion of all good and intelligent men about the late Tycho. Okay, so yeah, this guy was nasty. These two didn't get along because when Kepler first showed up to work for Tycho, this guy got bumped from the big project of Mars and it was given to Kepler. So from the get-go, these guys hated each other. Kepler replies to all this a year later, like these fights took a long time. Yeah. Kepler replies to him, he says, you discredit my elliptical paths. I hold up to you the 100 times more absurd spirals. The deference, the epicycles, the equins, all of that nonsense. That the spirals of the ancients, which Tycho imitated by not setting up anything new. If you are angry that I cannot eliminate the oval path, how much more ought you be angry with the spirals which I abolished? I am punished for leaving behind one barrel full of shit, although I have cleaned out the rest of the Aegean status. In other words, what do you want from me here already, Longo? I mean, I've done everything here and given you the simplest account possible, and it's still not good enough for you. Kepler went on to publish the Rudolphine tables, the magnum opus, the data of Tycho that allowed him, with his model, now to predict everything that was going forward. The most wonderful set of tables that were used in the 1600s and such. I threw in this name here too because I found out, to my shock and surprise, that some woman from Silesia, they're part of modern-day Poland, I guess this is, working on her own, came up with a much more simplified version of the Rudolphine tables that were much more easy to work with, and gets absolutely no recognition for this. She's just a clunky girl. Longo Montanus went through, he published his own material in 1622, so the argument was continuing here between Tycho's model of a fixed Earth and the sun going around the Earth and everything else going around the sun. That was Tycho's model. And so Tycho's model was still persevering in the 1600s. So long past even the death of Kepler and Tycho, their two models were battling it out for most of the 1600s. This is the Rundentarn that Longo Montanus had erected in Copenhagen as the new observatory to help prove the theories. So they were spending a lot of money trying to sort this whole issue out. This is an interesting character here that sort of sums up our whole story. And it's Robert Flood, or in Latin, it's Robertus Fluctibus. Anyways, he's this English Paracelsian physician. Paracelsus was one of the sort of modern revivers of modern medicine and such. And he had this very peculiar way of looking at things that said that this mathematical description of things that you think is so important, Kepler, is really insufficient to understand nature, let alone your little orbital stuff that's going on here. All you're looking at here are shadows on the wall. You're just looking at where things were, how fast they were moving. All of that sort of quantitative data is not going to get you at the truth of nature. You got to dig deeper. You got to do, well, we call it chemistry now, but for them it was alchemy. And it was with alchemy that you could throw in a few potions and have gold precipitated out. Or you had salts precipitated out. You were able to sort out the hidden nature of the universe here. And that's where you're going to get the reality. Not worrying about Mars being there at a particular time. That's not real science to someone like Flood. He thought that what Kepler was doing was just this sort of superficial stuff. That wasn't real science for him. He had all these ideas about the world, the universe at the time, having this structural continuity from very small things being mimicked at larger scales. Kepler just thought, this is just a bunch of nonsense. You've got all these crazy descriptions. You don't even know what symbolisms are doing and where they end and where your reality comes in with things. So I just want to leave you with a thought about what's going on in all of this. And that is, what is it about laws in physics that are so compelling to us? What makes them something of value that allows us to say, yeah, it does this because of a scientific law? And why do we feel compelled to find bigger and bigger laws? Why do we think that it's good to start working on ideas of theories of everything? And I'm sure most of you have read the magazines, have come across all these ideas like this and are wondering, what is the motivation for this? Why would something like quantum mechanics have to be integrated with our theories of gravity, for instance? Why do we need quantum gravity, etc., that somehow blends the two together? Can't we be content with two different descriptions? What is this urge to have a unified theory of everything? And what's going on with all that? Anyways, this whole idea of theories of everything, I think this would work really well with Kepler. I think he'd be pleased with that. He was also a practical man, though. I mean, here's a couple of issues that concerned him the most. This first, I confess that when Tycho died, I quickly took advantage of the absence or lack of circumspection of the heirs by taking the observations under my care, or perhaps usurping them. So he admits he stole the data. He took Tycho's data, just ripped it off, and he said, look, I'm the only guy who knows what to do with this shit anyway, so come on, I should have this. And as for his problem with astrology, here's probably the best quote ever. Mother astronomy would surely have to suffer hunger if daughter astrology did not earn their bread. Nobody paid him to do astronomy. He only got paid when he got paid to do the astrology work. And as a summation of what Kepler was all about, nothing holds me. I will indulge in my sacred fury. I will triumph over mankind by the honest confession that I have stolen the golden vases of the Egyptians to build up a tabernacle for my God. If you forgive me, I rejoice. If you are angry, I can bear it. The die is cast, the book is written, to be read either now or by posterity, I care not which. It may well wait a century for a reader, as God has waited 6,000 years for an observer. Even in death, Kepler suffered ignominy. He worked out a lovely little epitaph for his tombstone. Because of all the stupid-ass wars that were going at the time, some army came through the cemetery he was buried in and destroyed the whole thing. We don't know where Kepler was buried. But his last quote here, it's off the screen. This is the Kepler satellite that we've been using to discover all those exoplanets of late. But one of the things that Kepler said, and this was in conversation with Galileo, he said, ships and sails proper for the heavenly air should be fashioned. Then there will also be people who do not shrink from the dreary vastness of space. And I thought that's a fitting way to end the idea of where Kepler was all about. the movers, the wanderers. And the way they were wandering was against the background of stars. But did they do it directly by saying this planet was this far from that star? No. When you take a look at the instruments that Tycho had created at Uraniborg and Sternberg, most of what they were doing was making reference to an alt-azimuth system. And they were measuring that and then plotting that against the star and getting to... So Arcturus was at this altitude and azimuth at this time. Then he goes to measure the planet, and you get an altitude and azimuth measurement for that. They didn't do a direct thing. It was a much clumsier system to work with. The amount of geometry that they had to do to sort this out was just mind-numbing.
I've always been baffled about Kepler, that he managed to develop his 3 laws just purely from observation data. I always wondered how close was he to wondering about theoretical reasoning for developing his 3rd law, for instance, when I can't even balance the units on either side.
Yeah.
So I mean, I just wonder, how close was he when new to this? Was he thinking about the cause like gravity to explain all this?
Actually, yes. It went back to his ideas of the force, the magnetism out of the sun. Because of that, for instance, he said, okay, I understand the inverse square law for light. I mean, he had that all sorted out. But he said light goes everywhere. The moving force only went out in the plane of the solar system. So he said different mathematics is required to figure out the forces at that point, at the rate at which they dropped off. So he had that in mind, and some of his laws are actually like derived from that. I think in the case of his 3rd law, he actually comes up with that law and then looks to see if Mars, etc., were following it. So we kind of worked at it mass backwards there.
Regarding the 3rd law, did he ever address the idea that the mass of the planets in orbit would matter?
No, didn't get the mass. No, mass didn't enter into this stuff. Yeah, he didn't have to worry too much about that. All he had was something that really worked here. And in some ways, mass is a little bit irrelevant to it. You need to know, there is an equation there about, relative masses of the 2 objects and such. But no, you just need to worry about how far away it is and how it's going to orbit at that point. Semi-major axis, and so that's enough to get you what you needed to know. And I didn't mention too much about Galileo's reaction to that. If you let me come back and talk about Galileo sometime, we can get into that more. But with Galileo, he's like, Galileo knew everything about Kepler's work because Kepler was sending him message and book and everything going. I think Galileo wrote to him twice, maybe 3 times, mentioned him once in his works. And said, I don't need any of that hippie shit philosophy stuff that he's talking. I'm pretty sure if he was in modern time, that's exactly what Galileo would say. This stuff is just too weird. Okay, we don't need all this, this unified world that's singing in harmony with everything else. And forget that. Galileo was, and I.B. Conant in his book was saying that, no self-respecting astronomer, once he saw Kepler's notes describing, musical notes, describing each planet's hum, its tune, it'd back away in no time from that. That's just crazy shit.
Jerry, are you going to be giving presentations on the other ones as well?
Oh, if you want. I mean, Galileo's obviously the next one for this, and then would come Newton and such. But I don't know. Yes. My attitude about Galileo might get me run out of Dodge. He's everybody's hero, and I kind of consider him to be one of the biggest jerk frauds going. You want to hear that?
Give me the top down.
I really think. Okay, we must run away later.